I'm a second year PhD student at the business school. I'm studying data science, so that kind of keeps me in the loop with a lot of the statistics, math type stuff going on at the college. But I'm also Harvard College class of 2017, where I concentrated in statistics. Took a lot of these similar classes and have had some experience in this sort of course flow. So, this spring you may be taking Stat 111, you might be taking something else where you have to kind of code for the first time and use R for the first time. And that can be sort of a challenge, right? If you've never kind of coded before or used R and you're trying to learn like difficult 111 stuff, but also trying to learn how to code simultaneously, that can be tricky. So this session is just going to kind of walk through the basics of R, getting started, using it, and covering actually a lot of what you will see in 111. So I'm going to get started and share my screen. Obviously Zoom, we're all pretty good at the Zoom stuff by now, and I know Zoom meetings can be brutal, but just feel free to interrupt me. We want this to be engaging and interactive. Feel free to stop me, interrupt me. I'll try to ask questions to keep people engaged, but we'll kind of just go through everything. So what you see on my screen now is RStudio. And just to technically talk about kind of what's going on, R is the actual programming language that we kind of run our code in. Like you might have heard of C or C++. R is a programming language like C or C++, but the interface that we actually use to interact with R is called RStudio, which is what we see here. You can think of RStudio as just like, Microsoft Word or Excel or something. It's an app that it allows you to kind of play with R and do cool things. And whenever you load up the app, it kind of, if you haven't seen it before, it might look a little bit intimidating, but everything is super nice and friendly and comfortable. There are 4 panes. The top left pane is where we actually kind of write our code. I forget what it's called, but this is where we write our code and save it. And you can see I have some code preloaded here. The top right, this is the console. I think it's called the console, where we actually are going to run our code and kind of type things and do stuff. The bottom right, we'll have the files we're using, the plots that show up, packages, help, etc. And then the bottom left is going to show us our history of what we actually ran. So kind of the commands as we run commands, we'll see them in our history. But to start, like the best place to kind of start is just the top left in our file here. And this, what you're seeing here is code. And the simplest way you can use R, if you just like want to use a very basic like functionality for R, you can use it as a calculator. So I'm going to highlight this 4 + 4, and on my keyboard, I'm hitting Control and Return. You can also hit, I forget which one is run. Yeah, you can also hit this run button. So if I, highlight this or put my cursor on this line and I hit run, you're going to see that in my console over here, that code was actually run, which means it was executed, it was calculated, it was done by R. And here, clearly we just asked R, what is 4 + 4? And R said, well, that's 8. So even though R can do a lot of cool and really powerful stuff, at the end of the day, you can really just use it as a calculator if you want. And this is a good example showing like we can save code and type code in our files here. And then when we run it, we're actually executing it in the console. You'll also see that the history over here kind of has populated. So this shows us the last couple commands that we ran. Obviously, we just ran 4 + 4, so that shows up. So that's the most basic use for R. Another kind of very important fundamental is commenting code. So obviously, you're going to write code that kind of adheres to the strict grammar and syntax of the R language. But you also may want to comment your code so that a human can read it, right? Like you might see, for example, let's flash forward. You might see some, right now, this block of code looks like very intimidating and you're not sure what's going on. You might want to write a comment so that the human can see that it's just like, makes a nice plot for this, right? Like something that you wouldn't actually run in R, but something that a human going through can kind of remember. The way we signal that is with this kind of hashtag, this £. That basically tells R, ignore this line, don't do anything with it. And if I, go on this line and I hit run, oh, sorry. Yeah, that actually is not what I meant to do, but it worked. When I highlight this line and I hit run, it's going to just not execute. Like it will show up in the console, but it's not going to do anything. It's not going to throw an error. This is basically just saying run nothing. So simplest two functions for our calculator and commenting things. Okay, so now let's get into the a little bit more, I think, advanced, as you would say. when I started taking 111, I was basically just using R as a calculator the whole time. I would like, I would calculate, there'd be a problem with like 8 parts, A, B, C, D, E, F or whatever. And I would calculate the answer to A and then use that for the answer to B. And I keep going. And eventually you're going to have rounding issues, right? Like if you use 2.5 and then you round it to 3 for the, and you just keep doing it, it's going to be tricky. What's way easier to do is just save or values in variables. And in R, we call that assignment. And that's what this line is doing here. What's happening is we're putting the value 4 and we're storing it in X, which is a variable we're defining. And here you can see that the colors are different, right? Whenever we have a number, R makes that into kind of red or reddish pink in the look that I have. And these variables are colored white. So when I run this code, you're going to see it pop up in the console. You also see it pop up in history. And then if we looked in my environment, right, I'm going to see, okay, here's the variable or the value X, and here's what's stored in it for. And what's kind of tricky is that, we're not, this kind of operator looks a little bit weird. This is the assignment operator in R. And as far as I know, it's unique to R. Usually, you see equals, which, we see on this next line, but it's generally good practice in R coding to use this assignment operator instead of using the equal sign. Now, I talked to a lot of people about this. Maybe someone on this call has a better answer. It's sometimes it's tough to come up with like, why do we use this instead of just an equal sign? The way I think about it is that this helps you remember that 4 is going into X because of the direction of the arrow, right? And I know that seems dumb because it's like, of course, that's obvious. Like, why wouldn't, we wouldn't be putting the value X into 4. But sometimes when the code is really complicated and you have 2 complicated values on each side, it can be tricky to remember like, okay, what is being stored into what value? So that's one reason. Another reason is that equal signs are used for sort of different things in R. As we will see, they're used for logical tests. They're used for if statements. So sometimes when you're searching your code and you're searching for that part, it's easier to just search for an equal sign instead of searching for this operator. So those are the 2 reasons that I know of. It's annoying because it's like a couple of extra keystrokes. You have to hit shift to get this less than sign. Then you have to hit the hyphen. So it's like 3 keystrokes, but that's, proper syntax in R. It will work if you want to do this equals. So if I run this y equals 5, again, you see it pops up in the console and you see pops up in the environment. And now if I just print X and run X to the console, you'll see it prints 4. So let's do our first bit of interaction here. What happens? I'm going to highlight this X times Y. When I print it to the console, what value should I get? Don't worry, it's not a trick question. Okay, see it in the chat. 20. Nice. Thank you, everyone. Awesome. Yes, we got 3 correct answers. We're going to see 20. I run this and I get 20. And, another thing that I should note is that like, you can sort of get a sense of like proper style in R. If I just type this X times Y, this would give me the same result, but it's a little bit more cluttered, right? It's harder for the eye to see that this is X, times Y. So you always want to have nice spaces in between your operators. You want to spread things out. You want to keep them on different lines. So it's kind of easy for the human to read. Okay. So now just a couple of other housekeeping things before we get into, some of the more advanced stuff. R has a ton of packages and libraries in it. We'll talk more about that when we actually use them. But the idea is that people have built these really powerful tools and functions and abilities. They save them in these things called packages. And when you want to activate them, you call them with the function library. We're not going to talk about functions too much now. We're going to talk about that soon. But the idea here is we have this really awesome package, which we'll use today, ggplot2. It's really helpful in making visualizations. And this loads it into our session. So now we can use functions from ggplot2. Awesome. Okay. And then the last thing is if you are ever not sure what something means, you can always type question mark and then the function. So the mean function, it takes the average of something. We're going to use it a lot. If you are ever curious, you could Google, or you could just type question mark mean, and you can see automatically on the bottom right pane, this help tab was activated. And now you can read all about the mean function if you want to. So those are some other cool properties of R. Okay, any questions in the intro stuff before we move into loops? You can talk or you can chat, either one is fine. Okay, no questions. Awesome, sorry. This bread is chewier than I thought. Okay. So we're going to talk about loops in this session. We're going to talk about for loops and while loops. This is very fundamental in any sort of computer science, any sort of programming. You definitely will use it a lot in 111. Kind of as your coding career sort of, ages on, you may turn away from loops, but it's very, very useful and important and fundamental when you're starting out. So now we're going to get into some of the more advanced topics, and we're actually going to see code that looks like code that you might write in for a problem set or something. So the first line here, this is a comment. Remember, this is the R will not run this, or it doesn't do anything. This is telling. Oh, I see a chat. Yeah, I'm blank. That's a really good question. I'm blanking now. So the question is, shows a console tab and a terminal tab. What's the difference? Yeah, that is a really good question. I don't. Okay, well, I'll answer Henry Moss in a second. The terminal tab, sorry, Lorenzo, I want to look at your actual session. I'm not sure. It might be just like the terminal, just like at your computer, but I'll look at that. It shouldn't be a huge difference, but maybe it's like an environment or working directory thing. But sorry, I'm not sure. And then Henry, how do you get to the dark mode? Really good question, because when you load up RStudio, it's like it's very ugly and it's super bright and hard to see. Yeah, exactly. It's the essentials. So you go to view, or wait, it's been a while. Yeah, you go to tools. Sorry, tools, global options, and then console, or no, appearance. And then you can pick whatever you want. Yep, thank you, Skylar. That's exactly right. So we'll talk about that in a sec. So here you appearance, and then you can click on whatever you would like. And I have Cobalt, and then you're good. You're going to be spending a lot of time coding, so you generally want something that's like easier on the eyes here. So in case that you missed that, that's tools, global options, and then appearance. I'll just type it in the chat. Tools, global options. And as Skylar mentioned, terminal is like broad computer system. You can run code through that, whereas the console is just R. All right, very good, very good question. So returning to this, this first comment will tell us that we're going to actually initialize a vector, and a vector is just kind of a group of elements kind of grouped together. I'm going to run that here. You see, we're storing something in X, and here we're calling a function, and this function is called rep. So first of all, like this is the general function syntax. It's kind of like a workhorse object. It's going to execute some bit of code. It's going to do something. And you can tell when we're calling a function when we use the parentheses. So this is basically saying, call the rep function and then, do these things with it. Rep stands for repeat. They just, shortened it. So, it's easier to type. And essentially, each of these objects are arguments in the function. So the first argument is telling us what to repeat. And here I'm repeating this object that's NA, which we'll talk about in a second. And it's saying repeat NA 10 times. So if I just print out X, you're going to see there is 10 NAs. And you can interact with X, however you like. You can take the 7th element, it's going to be NA. You can take the first 5 elements. The way you do that is with this colon operator, and that will give us, the first 5. If I try to take the 12th element, that will also give me an NA, because there's no 12th element that's saying not available, but that's that's a little bit confusing. So just ignore that. We'll talk about that soon. The reason we fill X with NA is because we are going to do stuff with X. We're going to put actual numbers into these different elements. If we miss, let's say we miss one of these elements, right? Then it's very obvious that we missed it. Like imagine if we said X 1 through 9 is 9. Here, if we ran this whole thing, it would be very clear. Oh, we missed one. This is NA, right? This is not, it's easy to spot if we made a mistake. Okay, so that's why we do NA, so we can kind of fill stuff in that way. And again, if you are not sure, when you see a function called rep, you can just do !rep, and this, really good replicate elements of vectors and lists. So you're just repeating stuff, and you can see the usage. Arguments, again, this X is what you want to repeat, and then times is the number of times you want to repeat it. So you always have that available to you if you're not sure. Okay, so that's what X is. Now we're going to go to the actual loop part of it. So what a loop is doing, it's kind of a simple idea, but it can get more complicated. It's looping through a certain amount of times and doing something each time. This is a for loop, and you can see it's called a for loop because we type for. And the reason it's a for loop is because we're looping for blank number of times. You can see immediately that for is a special word in R because it turns orange, which is a different color than we've seen, as well as in, which we'll talk about in a second. And you always want to read the comment above the code. This is saying loop 10 times, set x equal to the increment. So let's see what that means. For is kind of a function here because we have this. I think it might technically be considered a function. We have these parentheses that are telling us what to do, and this is saying for I in 1 to 10. So what this tells R is every time we loop, we are going from I. We're starting with I equals 1, and we're going from I equals 1 to 2 to 3 all the way to 10. The reason it's 1 to 10 counting by 1 is because if I just print this 1:10, this is just saying for I in this vector. So I starts here, I then goes to here, then goes to here, then goes to here. We could count by a half if we want. We could go backwards. We could make bigger jumps, but we're saying for increment with I as values in this vector. Okay, so that's what we start. Then we have these curly brackets, which actually are like inside the curly brackets. We actually do stuff. We actually run code. So we only have one line of code here, and what we're doing is we're subsetting into X. We're subsetting into X with the address or whatever, the index I. So you can imagine on the first pass, we're going to have I equals 1, right? And then we're going to remember the I equals 1 is ignore that. I equals 1 is going to be the first value of X, and we're going to assign I into it. So it might be a little confusing. I'm just going to run this, and can someone tell me what X is going to look like when I print it to the console? You can put it in the chat if you want. Nice. Thank you, version. That's exactly right. So when I print X, I'm going to get 1 all the way to 10. And the way you can think about this is thinking about each loop through the for loop. So the first loop, basically I equals 1. So what the computer is running is this. The first element of X is going to equal 1. In the second loop, we're setting the second element of X equal to 2, and so on and so on and so on. And we're going all the way from I equals 1 to I equals 10. And that's how we get this X at the end. So hopefully that makes sense. You can always like collapse for loops. So here, you're saying this kind of is a cleaner way to look at it. For we're looping from I in this vector, and then we do some stuff in the curly braces. We run some code, and in this case, this was the code that we ran. Generally, this code is in a for loop is going to have to do, it's going to be some function of the increment I, which kind of makes sense because we're changing I. We want to, look at something in relation to I. So this was the next line, printing X, as we saw, it's just 1 to 10. And obviously there are easier ways to do this, but in this case, it was nice to kind of just do the for loop. Okay, so let's do a slightly trickier for loop. We're gonna, I see a chat. If you wanted to count by a number other than 1, yeah, great question, Jude. So if you wanted to count by a number other than 1, how would you do that? So, Jude is asking, like, here we have X from 1 to 10. What if we wanted to do from 1 to 3 to 5, etc.? What you'd have to change is the vector that you're incrementing, that you're changing I over. So let's say I just define this V sequence. I'll explain what this means in a second. And like 2. Yeah. So here, this function is called sequence. It means we're creating a sequence, and it's a nice interpretable arguments. So we're starting from 1, we're going to 10, and we're making the jump. A jump of 2 each time. Let me go from 0 to 10. So that kind of, I actually have to do 1 for 10 because it's not 0 indexed. Sorry. So here, V is just the odd numbers, 1, 3, 5, 7, 9. And now if I want to increment over that, I can just do, and this is kind of tricky, I can say I in V, right? This is saying iterate I over or in, the values of V. So the first time I is going to be 1. The second time I is going to be 3. The third time I is going to be 5. So if we ran all this code again, you're going to see that, the first value is 1, the third value is 3, but we didn't touch these in between values because V, there's no 2 in V, right? So we never touched the second index of X. So, this is a good example of why NAs are nice, because we'd be like, oh no, I missed some values, but this is how you would do it if you wanted to say, okay, you define another vector and then you would put that vector as what you're looping over. So hopefully that makes sense. All right, let's do a slightly trickier for loop. So I'm going to create a path here for Z. Again, this rep command is just, repeating the value NA. Now we have 100 times, so Z is much larger now. We have 100 elements of Z. And we're gonna do a random walk. So, you've heard of random walks in 110 or the Gambler's Ruin or something like that. Here, we're going to do just like this Gaussian, very simple, normal random walk. And we're going to start with the first value. So the first element of Z, we're going to assign a random normal draw. This, again, is a function that you're going to use a lot. This is saying draw a random value from a normal, aka R norm. All the fun distributions you learned in 110, there is an R version of them. There's an R binomial, like R binome. There's an R gamma. There's an R beta, etc. R norm is obviously the most popular, and or maybe not the most popular, I don't know. But this is really nice because we just have one argument here. If I pull up the help for R norm, you'll see the normal distribution, and you'll see that it has 3 arguments. So this is kind of a good learning session. It has 3 arguments here, and I only have entered 1. So it has n, it has the mean, it has the standard deviation. I've only entered 1. So this is just saying n equals 1, make 1 draw. Can anyone guess why I didn't have to put in the mean and the standard deviation here? Awesome. Yeah. Thank you, Samantha and TCQIA. That's right. Sorry, Brad. These are the default arguments. So when we define a function, this is saying by default, whenever it says, argument equals something, this is saying this is the default. If you don't enter a different number, we're just going to default to 0 and 1. So when we type R1, R norm 1, this is saying n equals 1, mean equals 0, standard deviation equals 1. If you want to change it, you can do like mean equals 3, right? Or standard deviation equals 10, but that will use the default. Okay. So that's the first value of Z. Now, if I print Z, I'm going to see my first value. I have this random draw from a normal and then a bunch of NAs. Now we're going to loop again. And here we're looping from 2 to 100. So again, this is a vector that goes from 2 to 100. This is what we're incrementing I over. Okay. And then, here's my code inside the for loop. And the idea here is we're starting, let's say we start at 2. So the second element of Z is going to equal the first element of Z because we have I minus 1. So 2 minus 1 is 1. So Z2 is equal to Z1 plus a draw from a random normal. I forgot to add the 1 here. So we're saying, second element, first element, plus random normal. Then the third element is the second element plus the random normal, and so on. So I'm going to run that. Can anyone put in the chat why I am not going from 1 to 100? I'm going from 2 to 100. Let me run it from 1 to 100 and see if that works. Got an error. Yep. Awesome. Thank you, Gerson and Heba. That's exactly right. So R, unlike a lot of other programming languages, is not 0 indexed. The first element in Z, we call the first element, which I think makes sense. I know computer scientists 0 index, whatever. In Python, we would say this is the 0th element. This is the first element, etc. If we say that I equals 1, we're saying, okay, set equal to the first element, the 0th element plus a random value. There is no 0th element. R is like, you're out of bounds. It doesn't work. And that's why we get this error. So error, it says replacement has length 0. That's just saying, you tried to do something that doesn't exist. So, it has length 0. So like if I try to print this thing, it's just saying it's a number, but it has length 0. It doesn't work. It's not happy. So that's why we do the 2 to 100. So we do this, and then I'm going to plot it so we can see the pretty numbers, and then we'll talk about it. So really cool now, we just started from not knowing anything about R to making this really nice plot of a random walk. And what's cool is that we can run this code over and over again and get different results, which we're going to talk about that when we talk about simulations. So let's talk about like what's going on with this code. R has some really nice default graphing parameters. You'll use a bunch in 111. We're also going to talk about ggplot today, which is even better, but the default stuff is good too. So we call the plot function. Obviously, that does plotting. The first element is z, which we just defined. And then we have a bunch of arguments. So it's going to be a line graph. The type is L. This is saying, actually forget what this is doing. Z lab equals I. I think that's defining one of the labels, but I don't remember. So let's forget about that. The color is dark red. The line width is 3. And then what's cool is I can add this this like A and B line, right? This is the, think about like the y equals mx plus b. This is AB line where, the y-intercept is 0. We color it black. We use the third line type, which is a dashed line. And then we use a width of 2. That gives us our nice dash line here. So this is kind of a cool, just a cool way to visualize. And again, we'll talk about more visualizations later. Okay, so that's all for for loops. Do we have any questions in the chat before we go on to while loops? All right, no questions, unless you're typing, in which case I'll wait a second. Okay, looks like no questions. Great. So now let's go to while loops, which are a little bit trickier, but kind of more exciting in a way. So the for loop gave us, what's really important in the loop is that every loop we're going to be going over and over and doing something each time. But it's really important to know when the loop will end. The for loop, that's very obvious. We're just going to go until I equals 100, and then we're done. With the while loop, we're going to run the loop while some condition is satisfied. Okay, and you see the same kind of syntax as orange while, and then within the parentheses, we're going to run this loop while this condition is satisfied. As soon as this condition is not satisfied, we're going to end the loop. Okay, and the condition here is x less than 3. And this can be important, like I didn't do this before, but if I just like had defined x beforehand as 4, or let's say I defined it as 0, then this loop would never run because right away x is less than 3. So let's just define x as 5 to start off. So this will run, and that'll make more sense in a second. So x is 5, so x is not. I messed that up. I knew I was messing it up. Let's say x is 0. So x is 0. X is less than 3, so we are going to enter the loop. Okay, so we enter the loop, and then we're going to do stuff in the loop. So in this case, we're going to draw some random uniform values. This is just like we saw the R norm. This is, random uniform. It's drawing a value of 1. And again, we don't have any other parameters. The default parameters are standard uniform 0 to 1. So this is just drawing random numbers. You can see like X here is 0.85, Y here is 0.12. And then we're going to have this condition. So, this is our original break condition, but we can also add conditions within the loop. And sorry, I'm getting ahead of myself. Can anyone just if we're focused on this code up here, what's the issue with this while loop? Can anyone see like a potential problem? Yeah, exactly, Albert. It never stops, right? We're going to run as long as x is less than 3, but the support of a standard uniform is from 0 to 1. So no matter how many times you run this code, x is always going to be less than 3, so this is never going to break. So, if we wanted to change that, we might make x less than 1/2 the condition. But otherwise, if we have like an unbreakable condition, what we can do is add an actual breakable condition in the loop. So here, we're adding this like if statement. We haven't seen these yet, but the idea is very similar. If, you can see it's an important word because it's orange, x plus y less than 1, then we actually break out of the loop. And again, another important orange word. So I'm going to run this code, and you can see the code has completed because I have this new like little arrow here. And if I type x plus y, what are the potential values I'm going to get here? Yeah, it's a good question, Sam. Y is defined in the loop because we're defining Y as a random draw each time. The only reason I defined X before was because we're using that as a condition, so I'm just making sure we have that defined. And Lucy, that's right. X plus Y will have to be between 0 and 1. There were 18 warnings. Let's see. I'm just curious what I did wrong. Oh, that's from before. Ignore that. Okay. So whenever I run it, we know that X plus Y will be less than 1. Here we got super close to 1, so that's cool. We're right up at 1, but we didn't quite hit it. But we know X plus Y would have to be less than 1 for this to indeed break. If I did something impossible, like if I said X plus Y less than -1, this is just going to run forever. So you see there's no arrow here. You see this like stop, it's saying if you want to stop your code, it's just running forever. I'm going to hit escape so it doesn't go. And here's a sense of how like fast R is. Let's set I equal to 1. Then every time that the loop runs, we're going to add 1 to I. So let's just run this thing. Let it run for like a couple seconds. It's not working. Hit escape. Give me a guess in the chat how big I is. Okay, let's see. So 10,000 seemed like a good guess. 583,000 times it went through this loop. So R is super powerful, running super fast, and that's why you have to be careful sometimes. If you don't have a good break condition, you'll just make R, spin, which is fine. R doesn't get tired, but I wasn't expecting it to be that large, so pretty cool. Okay. Any questions on the loop section before we move to the next part? ggplot. Cool. Awesome. All right, let's do ggplot. So we just saw a cool way to make visualizations in base R, and that's nice. That's really great. But ggplot is a really powerful visualization package that makes much nicer, much prettier plots and visuals. So definitely something worth knowing. Okay, so actually this might be. Do I want to do simulations first? No, we want to do ggplot first. Okay, so we're going to talk about what this code means a little bit more in the simulations part. Basically, the idea here is like, yeah, I'll talk about it more in the simulations part because it makes more sense. This is saying we're going to get replicable results, so we're going to do the same results we run a bunch of times. We'll talk more about that when we do the simulations. And now we're going to initialize our data. So here we can start to see the functions getting more complicated, multi-arguments. The function here, we're assigning something into the variable data. The function here is matrix. Okay, so this is creating a matrix. The first element is the first argument is telling us what the matrix is actually going to be. And this looks complicated, but it's just a random exponential. So remember the expo, memorylessness, etc. And here I have a couple of parameters. This is saying the number of times. I don't know, I did 10 times 5. You can just write 50. We're saying 50 draws from an exponential with lambda equals 1/2. So, that might look like this. Here's all the draws. There are 50 of them. And because I don't want to deal with all these fractions, I just wrapped that in a round, a function called round, which rounds it to the first decimal. So here, if I run this, I just get all these values rounded to the first decimal. Okay, so this is what we actually want to like cast into a matrix or create a matrix out of. And then these next two arguments tell us how many rows and how many columns the matrix is going to have. Okay, so if I run this is saying number of rows is 10, number of columns is 5. I run this. I don't know why there were warnings. Let me see. God, it still is giving me warnings from that plot stuff. R takes a long time to forget. So here, when I run this, we haven't seen this data type before, but hopefully it's pretty familiar. Clear my plot here. It's not very happy. Okay. Hopefully this is familiar. We just have like a 10 by 5 matrix. You definitely seen this in linear algebra if you take a 21B, but it's pretty intuitive. The ninth row, second value, so the 9, 2 entry is 13, whatever. This is just a collection of numbers. And again, we specified it had 10 rows and 5 columns. If we wanted to transpose it, we do 5 rows and 10 columns, and then you get this value. Okay, so that's our data. The next thing we do is this. Oh, I see chat. Yeah, sorry. That's a really good question. The way I'm running this, I'm sorry, it slows it down too, and it's nicer. You can always run it by clicking this, this little run, but I'm doing control return on mine, but it's a Mac, so it might be different. But I'm like highlighting the code, control return to run it. But in this, I will try to like actually click the run button because I know you obviously can't see me running it on my computer. So good question. Okay. It's kind of hard to click it though, because the Zoom thing is up there. Okay, run. All right. So this next function is cbind. What this is column bind, column space bind. So it's binding the columns together. We also have rbind, or binding the rows together. Cbind is column bind. So I'm taking this new column, which I'm calling numbers from 1 to 10, and I'm binding it to data, to the data object we have. And if I print this, you're going to see that, this is what I mean by binding the columns. So we took this column 1, and then we binded it to this data by kind of squishing the columns together. If I did a row bind, then instead of squishing the columns together, I'd be adding a row on the bottom here, right? Column binding the columns, we're squishing the columns together. Binding the rows, we're just like tacking them like this. And notice, because I have 1 to 10 as the first argument in cbind, data as the second argument, we put this 1 to 10 column on the left instead of the right. So that's the idea of what we have here. And the reason we're going to add this is going to become clear. Okay, so now we have this nice matrix. Another really useful type of data frame object in R is called the data table. I don't think I have the library in, which is a good learning moment. So here I tried to run this function data.table around data to create a data table, and it said error in data table data, could not find function data table. Whenever you see a could not find function error, that means that you're calling a function that is not included in one of the libraries currently loaded in your session. So what you can do is you can do the double question mark data table. R is going to think, and it's going to say, okay, what package is that in? And it's going to give you the search results. And it takes a while to kind of understand kind of what's going on here, but this is saying, okay, the data table arguments and all its like offspring arguments are in the data table package. I see your question. I'll answer it in 1 second. So you could also Google that. You could say like, what package is the data table function in? In this case, it's data table. So you call library data table. It's going to give you some information like, nice, okay, you did it, great job. This is a Mac. Please read this, whatever. But now you can actually run this data table function because it's loaded into your space. Okay, see the question. What's 1, 5, 9, 5? What's 1? Oh, yeah, sorry, really good question. This 1 over 5 is just 1 divided by 5, so it's 0.2. Yeah, sorry, it's a good question. That's the way we make a quotient in R, but it's kind of annoying that I did that. Maybe 0.2 would have been clearer. So really good question. Okay, so we created a data table, and the nice thing about data table is it already looks cleaner than the matrix. Like when let's look at the matrix again. It kind of has these just like indices and elements. When I run the data table, all I'm doing is creating a data table. Now I have like these nice rows with colons here. I have automatic names. They're not very creative names, but they're names of the columns. V1, V2, etc. And I can set names by running this names function. It's saying assign to the names of data, these different names. So here we said the names of the data table are going to be Day, Matt, Tom, Sam, and Tony. That's the names of my family. So and if you like did the wrong number, like let's say you missed one, with the very clear error, you can't assign 5 names to a 6-column data table. You need exactly 6 names. So that's how we so already our data table is looking much nicer. Okay. And we can view it, whatever. So this is probably how humans are used to looking. This is usually how humans are used to looking at data. And this is something that like is a very comfortable format in something like Excel. ggplot, and the biggest reason that ggplot is a steep learning curve and not everyone uses it is because it requires you to kind of transition the data from this long format, or sorry, this wide format to a long format. And what do I mean by that? We're going to call this function. Oh, I see a question. Really good question. Can you name the rows like you name the columns by heap? Let me see. Yeah. Oh, sorry. Let's see if I do this. Yeah. No, you cannot. Okay, that's a good question. Yeah. Okay. So this is a really good question. Data frame, which is also very popular, you can really nicely name the rows. It looks like I was able to name the rows, name them 11 to 20, but it didn't show up. So maybe it's like stored in the table and you can reference it that way. But I mean, you see another question. Oh, and yeah, so I'm not sure if you can do the row names, so that's a good question. But data frame you would be able to. Okay, good question about the library data table. So someone got an error saying there's no package called data table. So first, but even before you have to call library data table every time you want to use the data table function. But maybe you don't even have like the library installed on your computer. So the way you're going to do that, and sorry, I should have talked about this, is with this code, which I will put in the chat. Install packages in quotes the function you want to install. So in this case, install packages data table. This actually installs like data table to your, no worries, no problem. This installs data table into your session, and then you can call the library on it. Okay, good question. Should have went over that. All right. So now we're going to run this. We're going to convert our wide data into long data, which is why I have it called, I'm just going to rerun everything, why I have it called data long here. And I'm going to use this function melt. And what that's going to do is it's going to take the wide data table and melt it down into a longer data table. And we're going to melt it around the day column. So let's just do that. And we're going to see what it looks like. This head function allows us to look at the first couple, elements of the data table. Here we're saying look at the first 15 elements. So let's go ahead and look at it. Okay, so this clearly is already, here's our wide data table. It's not as long, but it's wider. This is much skinnier, but it's much taller, right? It's only 3 columns. This had 6 columns. It's only 3 columns, and it's a different format. You can see here, like the leftmost variable is giving us the day, and that's important because we melted around day. So now day is kind of the thing that's incrementing, and then it tells us the variable. So the variable is basically, the column name from before. We now see it 10 times, and the value for that day. So this is saying on day 3, Matt's value was 0.7. Maybe he walked 0.7 miles or something. On day 5, Tom's value was 5.2. And, if I print out the whole data long, you can see how long it's 50 rows long because it has 10 for each person. This is obviously not something that humans really enjoy looking at because you have to scroll down. It's not as good of a summary, but this is really, really nice for ggplot, as we're going to see. Okay, so now let's actually go to the ggplot side. What's cool about ggplot is you're adding, it's like a canvas. You like add bits and pieces on top of each other, and you start with the most basic, and then you just kind of add things on. So the most basic ggplot is just a kind of blank plot. And this happens when I run ggplot with parentheses. It just puts a blank canvas down. And it's like, okay, start creating stuff. The functionality is you use this plus sign to kind of link the commands together. So you add on to ggplot your gg title, and you're going to see gg all over the place in ggplot. So this just means a ggplot title. Obviously here it's going to be first ggplot. So there we go. We have our first ggplot with nothing on it. Now we want to actually add some data. So the way you add the data is you go to the ggplot function and you add the data in there. Your first argument is data long, which again, we've talked about is this long data set. And the next argument, and this is kind of where, it's a little bit confusing. It's not as clear as the R base stuff. First argument, or the second argument is AES, that stands for aesthetics. And that's telling you what your X values and what your Y values are. So here your X values are going to be day and your Y values are going to be value. So if we remember the data long, these were the days and these were the values, right? So I'm going to run that, and I'm going to get not yet. ggplot is really is taking its time here. You're going to see that I didn't technically say put any lines or points down. I just said this is going to be the data that we use. So it's all ready for me. It's like set up all the x-axes and y-axes, day and value, but it hasn't actually drawn anything yet. So let's actually print out our first ggplot, and then we'll talk about it once it's on the page. Here it is. That looks great, right? Like I think this is very cool looking, and this is why ggplot's nice. This really nice color palette. Everything looks very clean and fancy and nice. And let's talk about what's going on here. So first of all, you can see just like before, we're adding different elements onto the ggplot. The first line is the exact same as the previous section, except this color equals variable thing. And remember, with the long data, we had this day, we had the value, and then we had the variable. The variable is telling us which person, which variable, which object it belongs to. So, you can see here the variable, that's the, we're colored by variable. The variable are the people's names. So the matte line is this like reddish line, and you can see it here on the chart, right? And this tells us that we have different variables. We want a different line for each variable. We want to color the different lines by the variables. Okay, so hopefully, again, that all makes sense. And hopefully this makes sense why the data long is in this kind of weird format. We have the days, we have the values, and then we want a different line for each of the variables. That's kind of what's going on here. The geom line actually allows us to put lines down. So this is, I don't know why it uses the prefix geom, but this is saying draw the lines. If I did geom points, it would draw me points instead. So here you can see points instead of lines, which is also nice. This alpha equals 1/2 is telling us how dark the lines or points should be. 0 means they don't show up at all. 1 means they show up as normal. Here's our GG title, which we've talked about. This is the geom smooth. And what that does is it automatically adds a like smoothed trend line, right? So it just looks at the values and takes like an average or something. There's different ways to do it. You can make a linear trend line here. Obviously the trend lines are not linear. I have this SE equals false command. That's because by default, if I just run this, you're going to see that there's confidence intervals around the lines, which are kind of annoying. So you set the SE, which stands for standard error, to false. Another thing you could do, if I wanted to like put this in the background and make the points darker, I could just set the points alpha to 1 and it actually didn't work. So I had to figure out why, but you can make this geom smooth less dark. Then we add a label for the x-axis, which is days, a label for the y-axis, which is miles traveled. You can see that on my chart. We're going to add a y-intercept line that intersects at 0. That's this nice horizontal line here. And then we just add our I didn't need to do that. I don't want the title here. We add our theme here. This is the black and white theme. So theme BW, which like just gives like a certain type of look. Like you can do, there's like a 538 theme. I think this should work. No, can't find it. There's a lot of different themes that you can. Let's see what we got here. Let's do the void theme. Right, so this looks obviously quite different from before. You can do a dark theme. So the background here is dark. So a lot of really cool like ways to customize your plot and see what you like. So hopefully this all makes sense. Okay, any questions on ggplots? We're going to take a quick break too before we go to simulations. Awesome. So I'm going to just get up and stretch my legs for a second, and then I will be back in a flash. So get up, stretch your legs, and we'll be back in 2 minutes to talk about simulations. All right. Cool. What are some classes? Say in the chat what some classes people are thinking of taking this semester. Just curious what the fun new classes are. No classes. Good. CS 124. Nice. Tough class. I hear it's very good. Oh, what's stat 117? CS 181. Nice. Skylar is involved with 181, so it'll be good. We like to, yeah, exactly. There we go. What is stat 117? 111, 124. That sounds like a very sophomore spring workload. 111 will be chiller than 124. I'm just gonna, well, I don't want to mess up my shared screen. I'm curious, can someone just type what 117 is? Biostat. Thank you, nice. So I'm a PhD student, but they make me take like a million classes. So I'm kind of like, I kind of just take some undergrad classes sometimes to spite them because they just make me take classes forever. So I'm always on the lookout. Okay. All right. Let's get into this next section. We're going to talk about simulation. This is something that, you know, I did a lot in 111. I'm sure you will do as well. It's also really useful, like just in general. I mean, in 110, if you were able to simulate stuff, you could like check your answer. If this the mean of this random variable with this combination was something, you could always check your answer in R. Really good way to like double check. It obviously doesn't give like the theoretically correct answer, but you can see if your answers are reasonable. You know, when you learn Monty Python, you can obviously simulate the game and see like if you actually should switch and it actually works. So really, really powerful tool for R. We saw that R can do like almost 600,000 iterations in 5 seconds. So it's able to do something a ton, and you can kind of measure the results. So something you'll use in frequently in 111. Let's talk about the set seed thing. So when we say like simulating random variables or random values for the computer, you know, it's kind of tricky what we mean. And I'm not going to get into like the philosophical discussion of like what is random. Is everything deterministic? If you had all the data, would you be able to predict everything that I'm doing right now? You know, that's something for philosophy, and it's a little bit too scary like to think about for a stat class. So we're just thinking about like how computers generate random stuff. Obviously, computers are not random. They're programmed by humans, and they do, you know, sometimes it feels like they're doing random stuff, but there's always a reason for what they're doing. Which I guess may not be true for humans, hopefully, or maybe not. I don't even know. I'm getting into philosophy, so I'm just going to stick with this. So there's always a complicated algorithm in the background that is telling us how, you know, we are going to run these random numbers. And that complicated algorithm has a starting point, right? And if it'll start from somewhere and it'll generate numbers that kind of look random. And when I say look random, it means you know, they bounce around, but they follow like the distributional properties of stuff that we know. Like in the end, if we do it 1 billion times, it will look like a normal distribution, right? So that's kind of what I mean. There are like, that's a very intro discussion of it. There's a lot of like study and cool stuff on how to do random stuff, generate random numbers on computers, but that's kind of the idea. So this set seed is basically saying, where do we start with where do we start in the random algorithm? Let's say I do R norm 1, and I run that, I get 1.26. If I run that again, I'm going to get a different value. And again, I get a different value. But if I set the seed before, so let's say I set the seed, I got 1.26, then I set the seed again, I'm going to get the same value, 1.26, because the algorithm is starting in the same place. So what set seed does is it allows us to replicate, do the same, you know, thing if we're doing random stuff, and someone else can get the same result as you, and they can study it, and they can be like, oh, this is cool. So that's why we set the seed. Okay, so set the seed, and this is saying the number of simulations. We're going to do 10,000 simulations. Now we're going to do the bank post office stat 110 problem. So, you know, you hopefully remember learning about this, and maybe you're like, this is crazy. There's no way this is true. This has to be wrong. You can always go to R and check if it is true and if it makes sense and if the results kind of check out. So we're going to define the parameters. Here we have A and B as 7, lambda as 1, and then we're going to generate kind of the gammas here. So this is saying a random gamma value, 10,000 draws of each. The first is going to be gamma A lambda. The second is going to be gamma B lambda. Remember, gammas are just sums of exponentials. So this X is the sum of 3 exponentials with parameter 1. And this is the sum of 7 exponentials with parameter 1. So that's X and Y. And then I define W as the fraction, the percent of time, or the percent that is X. So, you know, if you remember, you kind of are like have you're waiting for the bank and you're waiting for the post office, and you're concerned about the fraction of time that you're waiting at the bank compared to the post office. So that's what we do here. And if you notice, like I'm going to look at my first couple X values. We're saying we did this 10,000 times. We have 10,000 different days here. On the first day, we waited 3.4 at the bank, then maybe 6 hours, then 3 hours, whatever. Same thing with Y. Y is going to have larger values, 4.6, 6.2, and then the same thing with W. This day we spent 42% of the time at the bank. So, that's this number plus this number divided, or sorry, that's not right. This number divided by this number plus this number. And this is the percent of time that we spent at the bank. And what's cool is like, these are huge vectors. They are vectors of like 10,000. But what's nice about R is that it's vectorized, right? It sees that X has length 10,000, Y also has length 10,000. So it's able to just like make these calculations by each point of the vector and then give us another vector of length 10,000 in the end. Okay, so, and I made a note here to notice vectorization. So here I'm going to run the correlations of each of, these different, so that's the core value or the core function. This is the correlation of W and X. So obviously the proportion of time that you spend at the bank is dependent to the amount of time that you spend at the bank. You spend a lot of time at the bank, your proportion is going to be higher. And you can see here they have a correlation of nearly 0.8, that is as to be expected. That makes sense. What was really cool about the bank post office, if you remember, is that the total time that you spend is independent of the fraction of the time, or the proportion of the time that you spend at the bank. So if I told you spent 20 hours at the bank and post office combined, you can't give me any information about how much time I spent at the bank. They're independent. And that's what we see here. We get a correlation that's close to 0. Again, correlation of 0 does not prove independence. This would not be a formal proof. It's also not quite 0. The idea here is that we're running a simulation to check our answer, and we're like, okay, yeah, it's a sufficient, not necessary condition, and it's close to 0, so it does look like, a little bit of randomness. It'll be a little bit far from 0, but this is basically 0. You wouldn't cite this as a formal proof, but it's a good intuition to see that it makes sense. Okay, so very cool that worked out. Now we can compare it to beta distribution, because if you remember, this proportion of gammas, has a lot of connections to the beta. That's something that, is big in 110, very big in 210. The connections of the two are really powerful. So let's compare this like W, which is the, X over X plus Y, to a beta distribution. And if you remember, is that the A parameter of the first gamma and the parameter of the second gamma are going to show up in the parameters of the beta distribution. So here I have R beta, generating a random beta. We put that at Z, and now we can see, Z has all these values. Again, they're going to be between 0 and 1 because Z is a beta, that's the support, and then we can plot our two results. So we'll talk about our ggplot in a second. This is basically asking the question, okay, is W, the fraction of time spent at the bank, does it have the same distribution as Z, which is just a beta? And you can see here, again, not a formal proof, they basically look the same. Here are a bunch of draws from each distribution. They very much overlap. They look like the same distribution, and this is a way to convince yourself. The code here that I'm doing is I put down the ggplots. So again, this, that's the first thing you do is just put down the blank space, and then we actually fill it in with values. This first line, we're creating a histogram. And again, we have this AES, this aesthetic. The X values are going to be Z, which are the betas we just drew. Here for histograms, it's not color, it's fill, because we're filling the bars. It's going to be red, and then 50% alpha, 50% darkness. Then we have the same thing with the proportion of time spent. I've added this theme command, which basically removes the legend. I'm saying, give them no legend position, because if I put in the legend, it's kind of ugly. You're going to see on the right, and it's confusing because I've defined like the fills as red and blue, but ggplot takes the first one and colors it red. So this is one of those weird, Bill Nye the Science Guy like tests where you're like, oh, can you read this even though it's red? So I take out the legend in this case, but okay. Cool. Any questions on simulation for the bank post office before we do the chicken egg? Okay. All right. So another really surprising result, I should not have started eating that, was the chicken and egg result. Okay, so the chicken and egg result tells us that if we have a Poisson number of eggs, so a random number of eggs that are hatched, say it's Poisson 10, and then each of the eggs independently hatches with some probability P. So the number of eggs that hatch conditional on the number of eggs there are is binomial NP. If that's true, then we're going to get a really cool independence result at the end of it. Conditional on, X and Y, the number of eggs that hatch and the number of eggs that don't hatch are going to be independent, which is really surprising, really weird, only works with Poisson distribution, yada, yada. So let's actually go through and generate it. Again, we're going to set up the parameters. This is saying that's not what I want to do. This is saying the probability that each egg hatches is 1/4. And this is saying that Poisson 7 eggs actually are laid. So there are on average seven eggs laid, but it's a random number. And then we're going to generate our N, which is just the, we're going to do a bunch of different days. And N is the, these are the values of the number of eggs that were laid on each day. So, it's easier to look if we look at the first day there were 4, then 3, then 8, et cetera, et cetera. That's kind of, our setup. Then we're going to set up our empty vectors for the number of eggs that hatch and don't hatch. That's repeating NA again, so we can detect we made an error, and sims times, which is, I think, 10,000. So those are setting up the empty paths. And then we're going back to our for loop. So obviously in simulations, you're going to be doing loops a ton, and this is a really nice use of the for loop that we learned. We're going to go from 1 to n sims. So I is iterating from 1 to 10,000. And each time we're going to do something, we're going to put inside the ith element of X, we're going to draw a random binomial value. Can anyone tell me what this line is doing? What are we counting here? Is this the number of eggs on a given? Oh, I see a chat. How many eggs hatch? Thank you, Vincent. Exactly. So each, the ith time through, we have n index I eggs. Then we're going to count the number of eggs that hatch with the binomial probability P each time. Okay, and the number of eggs that didn't hatch is just the number of eggs that we have minus the number of eggs that hatch. Okay, 3 1 out. One of the lesser cool results of the Poisson, the chicken and egg, is this Poisson splitting thing, where X, the number of eggs that hatch, is also Poisson with parameter lambda times P. So we can test that the same way we tested the beta, generate the Poisson with lambda times P, make some histograms to see. And you can see that, they're overlapping here, but the histograms are very similar. The blue and red distribution are basically the same. So, indeed, again, not a formal proof, but it very much looks like the X's of Poisson. And now we can check the really powerful independence result, which is saying are X and Y independent, run the correlation. And yeah, that looks very, very close to 0. It does look like they're independent, which is a crazy result. And again, remember, conditional on N, they are very much dependent. If we know, for example, here we're saying conditional on, N equal, which is one of those truth conditions. That's why we like using the assignment operator instead of the equal sign. This is saying for all of the X values where N is equal to lambda 7. So for all the X values where there were 7 eggs, these two are very, very correlated. Because if we know how many eggs there are, we know how many eggs hatched, we know how many didn't hatch. So can anyone tell me what value I'm going to get when I run this? -1. Exactly. Thank you, Vincent. Oh, that's not what I meant. So these have a perfect negative relationship. So the correlation is -1. Okay. Any questions on simulation before we go to optimizations? Awesome. Let's do it. Where is the chat? Unless I didn't see a chat. Everything is being, oh. Yeah, okay. All right. So I took 7-Eleven with Kevin Rader. We did a lot of optimization. I'm sure you'll do at least a little bit with Joe, because optimization is kind of a workhorse in statistical inference. So we're going to talk about that here. This will be our last like heavy R coding section. And we're going to start out by defining our own function. So we've previously worked with functions that are preloaded into R. You know, we like sequence has been one of them. We write the function name and then we call the parentheses. Sometimes you want to define your own functions because you need to get like a very specific thing done that no one's done before, or maybe they have done before, but it's not freely available. So the way you do that is you're going to define your object. A function is just like anything else in R. You're going to use the assignment operator. You're going to say the name of your function, and the way I like to do it is to start out with capital FUN. So we know that it's a function. We know it's not a variable. We know it's not a data table. We know it's a function. FUN underscore the name of your function. Here, this is just short for taking the negative square root, which is what this function is going to do. So the syntax here, we write function. Clearly, it's an important word. It turns orange. And we say what arguments the function is going to take. Here, it's going to be X. And then we actually, inside the curly brackets, actually do the work. So, here is the work we're doing. We are subtracting 1 from X, then we're squaring it, and then we're taking the negative of it. So, that's why maybe I changed this. But anyways, I'm just going to, I'm going to do a quick so it's not confusing. Ignore this. Okay, I'm just going to call this the mat function now because I think I changed it from what I was doing before. So the mat function is taking the value X, and then it's doing this. It's moving it by 1, squaring it, and then taking the negative value of it. This return, again, it's orange. It's important. It's telling us what we're going to return from the function, what the function actually spits out. So when we actually test it and we run function mat on 4, it returns -9. That's because we took 4 here for the X. So we did 4 minus 1 is 3. 3 squared is 9. -1 times 9 is -9. You can see kind of the order of operations inside the parentheses first, then we square. It's just PEMDAS. It's the same idea. Okay. Can anyone guess what's going to happen if I run funmat high with the quotations here? Some kind of error. That is right. It will be some kind of error because high is a character. It is not a numeric. And that is exactly what it's going to say, non-numeric to binary operator. R does not like when you try to do, number stuff with characters. So exactly, that is some kind of error. Okay, so we're actually going to calculate the output now. We're going to, we're going to do this function over a bunch of values. Here, we're going to do it from -10 to 10, which I defined with the sequence function. You could also just have done X -10 colon 10. That would have achieved the same thing. And now is an introduction to the sapply function, which is a really nice, powerful function that you'll use a lot. I think it has the same underlying mechanics of a for loop, but basically we're taking a function and we're applying it over a vector or over something else. So here, we're applying the mat function over the vector X. And it's kind of like a for loop where we're going through each of the elements of the vector X and we're applying fun mat to each of them. Okay, so I run this and I get Y. And again, what this is, like if I print out X here, I'm just going to make this full screen. This first value of X, that's when I run fun mat, that's what I get. -121 on -9, I get -100, et cetera, et cetera, et cetera. So I'm applying fun mat over all of these things. It should work too if you just did fun mat on X. R is vectorized, so it knows to apply this function over this vector all those times. But sapply is a good thing to just see, so that's why I included it here. Okay, we're going to collect the data in the data table. I just defined it. X as the X column as our X value, the Y column as Y value. And here we have this very nice and clean data table with the names already input, and we can plot it as well with our ggplot just to see kind of what it looks like. Here you see the aesthetic. The X value is X, the Y value is Y. We're adding our points down, and then we're adding our labels, our X and Y labels. Okay, so that's our data. Now, this looks like something we might want to optimize, right? We might want to find the maximum value of this function. This is a pretty easy example. You can point it out on a graph. You can do calculus to find it. You can even just do a grid search if you wanted to. But obviously, there will be many cases where manual or calculus or whatever is not as useful, and you want to use your computer to actually do all the hard work and search for an answer. That's why we use the optim function or optimization, which is what we're going to see here. It's kind of a complicated function, and I still have trouble with it even now. So it's annoying, but it's good to learn. The optim function takes in a function, which right here we name as the function mat. And if I just printed out function mat, it would tell us kind of what it is. It would tell us like what the code is doing. And this tells us a pointer as to where like the code is stored in R, but you don't have to worry about that. Par equals 0 tells us where the optimization is going to start looking. So it's always a good idea to kind of start, especially if you have like a really complicated multi-dimensional function. It's a good place to start where you think like the answer might be. Here, it looks like the answer is close to 0. So I'm just going to put in 0 because that looks like it's, it's close to right. This control equals list function scale -1. These, I don't want to get this backwards, but these, the optim really likes to minimize, but here we want to maximize. So this is saying just, flip everything, multiply the output by -1. So essentially this line allows us to maximize instead of minimize by multiplying the function by -1. You'll figure it out if you're getting like a weird answer that's giving you negative infinity. You're like, oh, just maximize this and allows us to do this. And then, we might say like, there's an area that we want to look over there. We know, we're pretty sure that, 20 is not going to be the maximum. So just look from -10 to 10 and that's good. And then the method, there's a couple of different methods you can use. We're not going to get into those, but, some will be better for certain situations, but Brent is like a solid one. So I'm going to run this. And then I get this scary looking output, but this actually tells us we're done. So this $par is telling us, it's short for parameter. It's telling us the solution, the parameter solution. It's saying that the value of x is, or the function is maximized when x equals 1, which we can see on this graph, right? You can see it's largest when x equals 1. This $value tells us that this is the value of the function when x equals 1. So here we have x and here we have f of x. This thing is basically 0. This is -4.9 with 32 zeros in front of it. It's machine precision, it's going to be a little bit off because it's like doing a search, but this, when you see this -32, this is basically 0. It will tell you, there will be a message if there was convergence, if it converged. I think 0 is good. I think a 1 would be bad, but I'm not positive. But the important things here are the par and the value, and that tells you that your function has been maximized. Okay, any questions on that? All right, no questions. So let's just move into, before we go just to the Q&A session, let's just move into Markdown. So, maybe, hopefully by now you're sort of kind of have a passing familiarity with LaTeX. You can obviously handwrite your problems and send them in. Back in my day, you would handwrite them on a piece of paper and staple the piece of paper and hand it in. So that's nice that you don't do it anymore. You can kind of scan it. But hopefully you're LaTeXing your problem sets, typing it up nicely. It's a little bit annoying to learn, but very valuable once you've learned it. Really easy to save stuff, clarify your thoughts, make stuff look pretty, and you're just going to be using it. So it's a good time to learn that. And maybe that's a separate session. Kind of the R answer to LaTeX is called R Markdown. It allows you to do all of the math typesetting, but also to interface R code into it. So here I have a Markdown file. If you want to create this, you just go to File, New File, and instead of an R script, which is what we've been working in, we can do an R Markdown. That's what I did here. And then you're going to see this cool results. This here is just free text. This is like you would have in your Word document, where you can type whatever you want. If you want to enter math mode, like if you're familiar with LaTeX, you can do $ mu equals 7 alpha plus gamma, and then when you want, and you can see this is the preview here of what it's going to look like in nice, typeface math. And now if you want to enter R mode, you're just going to do these 3 like little backwards apostrophe on the top left of your keyboard under the escape key if you're using a Mac. And then you use the curly braces with R, and then you entered R mode. You can tell that the shading is different, and now we have just R code like before. This is 4 times 7, storing 21 in X and squaring it. And if I press the play button here, it's going to run the R code for me locally, so I can see what the outputs are. and you can make a plot as well. So, once you've done all that and you actually want to see your finished product, notice if we went to the R script, we didn't have this knit command. So knit will allow us to, as it kind of says, put everything together and make it look pretty. I'm going to knit it to an HTML. I'm just going to put it together. Here it comes. I think that messed up my screen share, so I'm going to try to reshare it. Yeah, here it is. And now I have this nice, this nice kind of much better looking homework where I have some R code in the output here, R code output, but then I also have text, I have math mode, you can add links to stuff. So really nice. Something that's not, if you know LaTeX, your Markdown is very easy to use and super chill. And even if you don't know LaTeX, it's a good place to just weave your R code in instead of taking the plots and copying them and pasting them and putting them in the Word doc and doing all it. It's just a way nicer way to do it. Okay. So I think that's everything for me. I'm really thankful. Thank you guys for coming. I know it's like a lot of time and you're still on your break. I will stick around and do a Q&A, but thanks for coming and yeah, it's been great.
Yeah, thanks so much, Matt, for doing this as always. Super blessed to have you around, man.
Thank you. Thanks for having me, Skylar. You guys can stick around if you have questions, though. It seems like people are dipping.